mode.
Hello everybody, and welcome to today's webinar. This is part 2 of a 2-part series on AC mitigation. Today we'll be focusing how to mitigate AC and lightning effects. And I'm your host, Dan Levy, and today's presenters are Clay Brailsford and Jordan Garuti. Some quick webinar basics. All participants are going to be muted today. If you have any questions, please submit them in the question box in the GoToWebinar side panel. We will be recording today's webinar and it will be available via YouTube. Please be on the lookout for our follow-up email on access information. Today's webinar, we're going to cover a variety of different topics, from engineering controls, DC coupling devices, current drain points, gradient control mats, and coupon test stations. Today, like I said, I'm your host, Dan Levy. I'm a software product manager for American Innovations. And today's main presenter is Clay Brailsford. He has 30+ years experience in cathodic protection systems, including experience in design, installation, and maintenance of induced AC and lightning mitigation systems for pipeline applications. Joining Clay today is Jordan Garuti. Jordan Garuti is the Director of Business Development for Bass Engineering. With 8 years of cathodic protection experience, he provides technical solutions, advice, support, and training to a variety of clients across the oil and gas industry. With that, I'll launch our first poll of the day. What is your organization's current level of activity regarding AC corrosion and hazard mitigation? You have a variety of different options, from you've never heard of it or you have no known issues on your system, to you've heard of it but not actively working on solutions, or you already know you have an AC problem and you're looking for best solutions to mitigate this problem, or you have multiple AC projects ongoing and you're looking for best practices. So while you guys fill out the poll, I'm going to hand it over to Clay.
Good day, folks, and thanks for taking time out of your busy day to join us here. We'll be, again, talking through a number of topics in this second webinar, and if you participated in the first part, you were hopefully introduced to this AC mitigation world, and so today we want to talk a little bit more about some possible solutions that could be available to you as you experience that. Well, it looks like our poll results are in, and it looks like most of you have certainly heard of AC, and looks like roughly half of us have multiple AC projects and are looking for best practices. So probably a good bit of experience on the line right now, and thank you for that, and hopefully we will be off and running with maybe some new ideas for you to talk through. I think most of us would understand the threats posed by our coupled AC energy. Number 1, electrical hazard to personnel. Number 2, electrical isolation equipment damage. Number 3, pipeline damage. 4, damage to our coatings. 5, AC corrosion. And 6, CP system degradation. We want to talk through each of those in some detail and offer solutions for all. First and foremost, we need to think about personnel protection. That has to be your number one concern when you're dealing with induced AC on our pipeline systems. Second would be the pipeline and pipeline system equipment protection. And third, the interaction between your active CP system and the AC mitigation system. We have a number of devices in our toolbox, if you will, that are at our disposal to use as we tackle this problem. One of the simplest and most frequently used are rather standard engineering controls. So these can consist of signage, as well as dead front test station design. Right behind that, we start using a number of off-the-shelf products. DC decoupling devices are available to us. And then we want you to start thinking about current drain points. We may abbreviate that as CDP. Some people will refer to that as grounding. We'll try to differentiate between gradient control and grounding in this presentation as well. The fourth tool in our toolbox would be our gradient control mats in various configurations. And then finally, coupon test stations, sometimes used in combination with zinc anodes to establish drain points as well. Here are some examples of signage that you might find or you might want to adopt for your own uses. On the left, you can see pretty straightforward language. On the right, the little symbol there is the open palm with a lightning strike through it. Unfortunately, there's not any standard language that I'm aware of that's been established at this point. So anything that you can do would certainly help your own employees as well as the general public be aware that there is an AC voltage hazard in that area. When we talk about dead front test station design, we're essentially talking about some type of banana plug, anything other than an exposed terminal. So again, on the left, what you're seeing is the simple two-prong test station or two-terminal test station, but using banana jacks instead of exposed terminals. And then on the right, obviously there's going to be some Bass Engineering, American Innovations equipment in this presentation. This is what the Triton coupon test station assembly would look like if you chose to use that product. So it is a combination of the banana jack terminals all enclosed in a cover, so you have to intentionally open that test station and expose the terminals. There are a number of DC decoupling devices on the market. Some of these have been around for a number of years. Probably the first zinc grounding cells or the first decoupling devices that we experienced in this business were the zinc grounding cells. And you see just a material cut sheet diagram of that in the top middle. And that essentially consisted of two zinc anodes separated by a simple cardboard separator. Both anodes were enclosed in a single bag. Each anode had its own separate lead, and the way that they were designed to be used is you would connect one lead on one side of the insulation, the second lead on the opposite side of the insulation, with the idea that you created a low resistant path between the two anodes. The hope was that there was a high enough resistance that it would block DC, excuse me, but would certainly pass AC under a high voltage condition. They were somewhat effective. They have been replaced first with polarization cells. Again, you see a depiction of that in the top middle, also known as a Kirk cell. And then the other two devices, excuse me, the other two devices that you see are the polarization cell replacement on the far right, and then in the bottom center, a solid state decoupler. We'll use abbreviations for both of those, PCR and SSD respectively. The other tool that we have in our toolbox is current drains. Now, some of these current drains could be existing equipment that you have in place. So many times when you're considering some type of AC mitigation for your pipeline system, don't overlook what you already have in place. One of the more common grounding elements that's in place are our road and railroad casings. Many times these casings are electrically isolated from our pipelines. Obviously, we hope that they are, but you would want to verify that they are electrically isolated from your pipeline, and then you might consider using that casing as a current drain point or grounding point for that pipeline. The other existing equipment that might be available would be any plant grounding systems. And when we say plant, we're actually referring to any kind of processing facility, sales point, anything of that nature that might have an existing grounding system associated with it. And then finally, any bare pipe that you might have available to you in your system that you could couple to. Now keep in mind, any coupling that you do between your pipeline and that existing grounding, you're going to want to connect that through a decoupler. Remember, the purpose of that decoupler is to block DC power passage and allow AC power passage. So the decouplers are critical in these systems to provide that blocking function that keeps our CP system operating effectively and allows our AC mitigation system to function as intended. Now it's time for our second poll, and just trying to get a feel for where you folks might be in your own ACLM system designs. Have any of you used existing grounding equipment in your AC mitigation designs? And the choices that you see in front of you are simply yes, no, or possibly I don't know. So we'll give you just a minute to reply to that, if you will, and then we'll be off and running again. Just trying to get some sense of how widespread the use of existing equipment is in your AC mitigation system designs, and get some feel for how you consider that. So it looks like a good number of you are indeed using existing equipment in your system. For those of you, roughly 20% that answered no, and then another additional roughly 20% that don't know. Hopefully that's something that you might consider in the future as you look at your AC mitigation system designs. Additional grounding that could be available to us. So if we determine either A, that the existing equipment is not going to be sufficient to complete our design, our current drain points, or B, we simply don't have that available to us, then we may have to create those grounding points or current drain points. Those can take many different shapes and forms. The one that we're talking about first is a deep vertical point ground. So in this case, we're going to drill a hole in the ground. Generally, they're going to be in excess of 100 feet. We would use a copper conductor in that hole and surround that copper conductor with a conductive concrete backfill. The conductive concrete backfill does a couple of things for us. Obviously, it does provide additional conduction for our central grounding cable. It also provides intimate contact between that grounding cable and the surrounding soil, and it gives us the additional option of providing groundwater protection as a part of that. Once again, the decouplers are a critical piece of this system design. We do not want to connect additional grounding simply to our pipeline system, because we will destroy the design function of our CP system. So by using the decoupler, once again, we're going to block that DC power and allow AC power passage once we exceed the voltage limits as defined with those decoupling devices. Another way that you may think about additional grounding would be a linear cable ground. Generally, these are installed at pipeline depth, which is generally going to be something at 3 to 5 foot deep. Most often, you would see a copper conductor used in conjunction, once again, with a conductive concrete backfill. And once again, you see the decouplers at play to decouple that copper conductor from the pipeline for DC purposes, but enable conduction under AC conditions. There are other cable grounds that have been used in the past. Many of you may have experience with zinc anode material. Some people may have experience with steel cables. We've certainly heard of all of those. We would prefer a copper conductor in most instances. One other caveat that you want to think about with the linear cable grounds, many times each one of these systems has its own pros and cons. So you have to consider your right-of-way availability, you have to consider obstacles that may be in your way, but we found the linear cable grounds to be particularly useful in helping us create a shield between electrical substations and our pipeline. So as you can see in the simple diagram on the right, in this case we're indicating that we've used a limited linear cable ground installed between that electrical substation on the far right-hand side and our pipeline system. Again, the black diamond represents the decoupler that we would use in conjunction with that system. The little blue triangles that you see represented, we can augment that linear ground with vertical or horizontally installed zinc anodes as well, or even just additional copper in shallow holes. The point being, you're trying to establish a low resistance grounding path for that current, that stray AC current that might be present on your pipeline, and provide that path back to the substation. Note that the linear ground is between the substation and the pipeline. That is by design. You want to provide that current discharge point on the grounding or substation side of your pipeline. We're going to talk just a little bit about gradient control mats, but before we do, we want to talk about the anodes that are installed in conjunction with those gradient control mats. So many of us have had experience with gradient control mats, but one of the important parts of that design that you have to realize is those gradient control mats are going to be electrically isolated from your pipeline for purposes of cathodic protection. They'll be electrically connected to your pipeline for purposes of AC mitigation. So please don't forget that you will need to provide a separate cathodic protection system for those gradient control mats. Many times that cathodic protection system will consist of magnesium anodes. Again, for the corrosion experts in the room, understand that those gradient control mats are, in most cases, are going to be a zinc coated or galvanized material. So we're going to use a more active metal to couple with that to afford cathodic protection to the zinc. So most often you would find that to be magnesium. But you have to design the CP system to protect that mat. It is not a one-size-fits-all situation, no more than any CP system is a one-size-fits-all. So you have to be very deliberate about considering that gradient control mat, considering the surface area, considering the soil resistance, and design the CP system to protect that amount of gradient control mat material. Since you are installing magnesium anodes with that gradient control mat, go ahead and specify heavier cables on those magnesium anodes. Since those magnesium anodes could be expected to serve as a current drain point, you want to make sure that the cable has the current carrying capacity to handle that. Now understand, that is not their design purpose, but you should anticipate some fault current, some AC fault current, or induced AC for that matter, possibly using those magnesium anodes as a discharge point. So consider oversizing that cable. We would typically recommend a number 6 cable with an HMWPE insulation. So it would not be your standard number 12 THHN lead wire insulation that you might be accustomed to seeing on your magnesium anodes. Let's talk for just a minute about the difference in gradient control and grounding. To many of us, those kind of sound like the same thing, but they're not. Gradient control is very different from grounding, and maybe just anal engineers get excited about that, but it is important that you understand the difference so that you can correctly apply the various tools that we have at our disposal. So as we start this discussion on gradient control and grounding, it's important that you understand some terminology, specifically step potential, touch potential, gradient potential rise, and earth potential zone. So as you can see in the simple diagram that we have here, and I'm going to grab a pointer to help you with this just a bit. So in this case, you can see that we've depicted a high voltage AC transmission tower, and we have a couple of gentlemen moving in close proximity to that tower. Now what we're indicating here with the yellow dashed line is I want you to imagine a lightning strike on that tower. Now that tower is designed to move that energy to ground very, very quickly. So in the case of touch potential, if the gentleman on the right were to be touching that tower at the time that the lightning strike happened, it's entirely possible that some of that energy would choose his body as a path to dissipate that energy. So it's essentially a parallel path for that energy to flow to ground. Now, most of you could understand that, well, that's going to depend on the resistance of the hand to the metal, the resistance of the foot to ground. You are absolutely correct. All those things are true. But the underlying message here is let's not play around the high voltage AC transmission towers. They're designed, they're working. Let's not get around them while they're working, and they are designed to move any extraneous power to ground very, very quickly, whether that comes from a lightning strike or whether that comes from a fault on the transmission system itself. One of the other phenomena that you need to be aware of is in the case of a lightning strike, primarily a lightning strike, you can see very large amounts of current going to ground. As that current enters the ground, you have current passing through a resistance. We all know that to be defined as voltage. As that current moves through the ground, you will see that gradient potential rise or earth voltage gradient. There's a number of terms for that, but we will establish an earth voltage gradient in the ground. So that's what is created if you're standing next to that tower or very close to the tower. Your right foot could potentially, pun intended, be at a higher voltage level than your left foot. That being the case, and all of us understanding that a difference in voltage is what causes current to flow, you would then create a path for current to flow through the body. In either case, whether it's touch potential or step potential, those are not good for the human body. We're not designed to carry current through our body. So many times when you hear about a lightning strike, or maybe you've heard about a football team or a soccer team that was practicing on a field and they were struck by lightning. That's usually how the newspaper article will read. That's probably not what happened. Lightning did not descend from the sky and touch 10 folks on the top of the helmet. Most often, lightning probably struck the goalpost somewhere, and the 10 folks that fell down were affected by this phenomenon on the left, the gradient potential rise, which causes that voltage potential to exist between the left foot and the right foot, and there's enough current that passes that you fall down. And we're locked up here. Here we go. So just a little bit more about gradient potential rise and equal potential zone. what we're trying to depict here, if you can see the little footsteps on that diagram, and I'll try to help you with that. So once again, these are some typical values that you might see very, very close to the event. So it would not be unusual to see a 5,000 volt difference between maybe a span of 3 feet. So that term step potential, that's what that refers to. Again, here you can see another 5,000 volt difference, and then another one here. So it's critical that we be able to control those gradients near where those hazards could exist. So I'm setting you up for that great terminology that we as engineers use, gradient control mat. Again, we're not marketing people, so we tend to name things for what they do. So we didn't come up with a real snazzy name, we just called it a gradient control mat. Let me get the pointer out of the way. So what we're trying to show you here is this is a gradient control mat. This is what we're trying to depict here. And this particular gradient control mat is equipped with anodes. And those anodes are directly connected to the gradient control mat. Now, the anodes, again, they are not intended as current drain points. They might function as current drain points, but that is not their primary purpose. Their primary purpose is to afford cathodic protection to the gradient control mat itself. In addition, what we're trying to show you here is a flange installation kit that would be associated with a typical insulation point. So we're using a decoupling device here, the PCR, to offer protection to the isolation kit. In addition, we have to connect our gradient control mat to our pipeline. We're going to do that through a decoupler as well, in this case a solid state decoupler or SSD. So once again, what we're trying to depict is in the event of high voltage event on the pipeline, we can quickly dissipate that energy across the flange insulation kit, thus protecting the isolation status. We can also send some of that energy down to our gradient control mat so that the gentleman depicted walking up to the pipeline itself, you can see that even though his feet are apart, he's on top of that gradient control mat. So that gradient control mat serves to collapse those voltage gradients. So instead of a 5,000 volt difference between left foot and right foot, he may only have a volt or two. So we have effectively collapsed those gradients. The anodes may be assisting with the dissipation of some of that energy, but most of that energy will tend to dissipate right off of those gradient control mats as we collapse those voltage gradients in close proximity to the pipe. Once again, think about those gradient control mats. We must design our CP systems for the conditions that they're exposed to. So just like you would design a cathodic protection system for your pipeline structure, you're going to move through those very same steps for the design of your gradient control mat. So that would involve measuring soil resistance, calculating current requirement, and designing the appropriate number and size of anodes that are required to protect that structure. We have just a few slides to take you through those steps. In this case, you can see these are obviously some 20-pound anodes that are being used, and they're being we're using a foundation drilling rig to install these at something 20 foot or less in this particular environment. The gradient control mats themselves, they come in sheets, much like floor tiles, except that they're 4 foot by 8 foot, dimensionally speaking. So as you build your gradient control mat, you must interconnect those gradient control mats one to another. We prefer an exothermic welding process for that. So you can see on the right, the exothermic process results in the weld material, but as many of you are aware, we've now created a bimetallic coupling. So we have the weld material in contact with the zinc, our galvanizing material on the mat. So as soon as we do that, we've created a galvanic cell, so it's more important than ever that we have our anodes connected to the mats so that we can protect not only the mats but those couplings that we've created. The couplings need to take place about every 18 inches along the seam of the mats, so there are a number of exothermic welds that will be associated with any gradient control mat construction. Now you can help your CP system just like we do with our pipelines by coating that weld material. Most often we would use a wax tape product to do that. It's easily handled. It's moldable to that irregular shape that's going to be associated with that weld material. Here we're just showing you the magnesium anodes that were installed prior to laying the mats down. Now we're terminating those leads directly to the mat. We're trying to keep those leads as short as possible. Again, the primary purpose of the anode is not for current drain or grounding. The purpose of that of that anode is to offer cathodic protection to the mat. So even though keeping the lead short is extremely critical to our AC applications, in this case, we're simply trying to augment that system any way we can. So we're going to follow that guideline with our our anode leads as well. Once again, you'll notice this is not a number 10 THHN lead wire. This is a number 6 AWG HMWPE lead that we're connecting the anode to the gradient control mat with. When we're making connections with our decoupling devices, most often we're going to use some combination of exothermic welding or more recently pin brazing. The pin brazing technology has proved to be extremely valuable for coupling our decoupling devices to the pipeline, for attaching our decoupling devices to the pipeline. It's quick, it's easy, it gives you a great deal of versatility in attaching these decoupling devices to your pipeline. What we're showing you in this case is the SSD, or solid state decoupler, that we're using. And what I do want to point out is there's 2 tabs on that decoupler. So this tab on the left side of the decoupler is directly connected to the pipeline through a coupling nut. So while these connection links need to be really short, we work that to our advantage in this case by using the pin brazing technology and keeping that extremely short. Now the remaining 2 leads obviously are going to be connected to our gradient control mat down here at the bottom. If you're around an AC mitigation system or you're considering installing one and you're going to use these devices, once again, I cannot stress enough the importance of keeping our lead links very short. So if you've seen an AC mitigation system, you might wonder why those SSDs are so inconveniently low to the ground. The reason is we're trying to keep those leads very short. So yes, you're going to have to bend down to check them, and get down close to the gravel that's going to be associated with that above ground pipe setting. What you're looking at now is a completed gradient control mat assembly. So you can see the mat material that's laid out. You can see the SSD on the pipeline itself. In this case, the gradient control mat, what I do want to draw your attention to, the gradient control mat extends beyond the footprint or outline of the chain link fence that is there for security purposes around that valve. So if you can see that we've taken the fence fabric down, the security fence fabric is gone, that enables us to lay the mat all the way across and extend past that perimeter. The idea being, as the individual approaches that gradient, that block valve setting, at some point he's going to have to touch the fence, most likely to unlock a gate. Well, you definitely want that individual on a gradient control mat at that time in the event that an upset happens or a lightning strike happens somewhere on the system and there's energy being dissipated to ground at that location. You want to be controlling those gradients very effectively there. Again, you see the SSD. You can see it's mounted rather low to the ground. And then what you don't see is the finished product. There will be some 6 inches of limestone rock that will be installed on top of the gradient control mat to offer further separation from the individual and the mat material. And our third poll that we want to work with you folks on, you should see on your screen now. Do any of you employ cathodic protection design principles for your gradient control mats? Again, your choices are yes, no, and I don't have a clue. So any one of the three would be fine. Again, trying to get some idea of the level of understanding of our gradient control mats and how these animals operate and what we must do to offer cathodic protection to them. So it looks like our results are in, and just for the audience, I'm not sure if all of you can see those results, but about a third of us are considering some type of CP design, about an equal number or not, and roughly a third of us don't know. So once again, I hope that's you find that to be enlightening and educational, that we must consider cathodic protection designs for our mats so that we get a good long life from that mat material. I want to talk just a minute about our coupon test stations. We prefer to use coupon test stations associated with ACLM system monitoring for a number of reasons. These type test stations give us multiple ways to measure both the cathodic protection and the AC potentials, and thus the effectiveness of our ACLM systems on our pipeline. So using the Triton coupon test station assembly, you have the opportunity to use the DC functions of a coupon test station, but in addition to that, you get the opportunity to use a 1 square centimeter coupon to measure AC voltage, and with that, also with a current measurement, an AC current measurement, you can easily calculate the AC current density associated with the pipeline at that particular location. So the photograph that you see there on the right, that is a live Triton coupon test station in the wild. You can see the reference cell part of that coupon is buried. You're seeing the two 100 square centimeter coupons, and then at the very top of that device, you're seeing the 1 square centimeter AC coupon. The faceplate on that coupon is designed so that the testing can be done from the surface. Again, your reference cell is at pipe level, so you're doing a lot to minimize the IR drop. You're only going to measure the potential from the reference cell to the test coupon. You can interrupt that current much like any other coupon. And in addition to that, you can take a current measurement between the pipeline and the 1 square centimeter coupon that will enable you to calculate your current density at that location. What we're showing you now is a typical, or what could be a typical pipeline HVAC power line co-location. So I'm going to grab the pointer here and walk you through this. And I'm going to move left to right through this system. So obviously the power line is depicted with the little icons depicting our towers, and the solid blue line represents our pipeline. So as we move through this, what you learn from part 1 is that points of discontinuity between the HVAC power system and the pipeline can create voltage peaks on our pipeline, AC voltage peaks. So in this case, you can see the design has resulted in a deep vertical point ground at this first PI. Then we have an above ground valve setting. So we'll be using a gradient control mat there. We have another PI here at location D. In this case, the design has called for a coupon test station. Again, we're expecting a voltage peak there. So with that peak in voltage, we would expect to see a peak in AC current density as well. And so we want to monitor that. As we cross the HVAC system, you see another point of intersection. This particular design is calling for a deep vertical point ground here. And then we've conveniently located a road crossing with a casing. So we're going to incorporate gradient control mats and connections to the casing here. Again, remembering to use our decouplers as designed. We have another coupon test station at this point of intersection, another coupon test station at this point of intersection, and finally another valve setting with flange insulation kits installed. So we'll be using gradient control mats, we'll be using PCRs across that flange insulation kit to offer protection there. And again, the gradient control mat offering personnel protection as well as offering some limited current drain point. So you can see, obviously, yes, we drew this. Yes, we can create it for academic purposes, but hopefully it gives you some idea of how you can design and utilize an integrated ACLM system to your benefit. So you're using not only the natural existing grounds that are present, but you're also using all the tools in your toolkit to your best advantage to help you not only mitigate that AC voltage and threat to personnel, but give you some way to monitor that going forward. Finally, we would be remiss if we did not give you the technical references that are available to all of us. A number of these come to us through NACE. So if you choose to use coupon test stations, it would be great if you at least scan through the technical report on the application and interpretation of data from external coupons. There's also the AC corrosion state-of-the-art report that's been out for several years now. The reference to 49 CFR, that's where you find the impetus for federal regulation for these systems. NACE SPO 177-2014 that was just upgraded a couple of years ago. And then finally, understand that there is a NACE task group that's currently working on a standard that will be titled AC Corrosion on Cathodically Protected Pipelines, Risk Assessment, Mitigation, and Monitoring. So that one has gone through at least one round of voting, and we'll be proceeding through the process in the next few months. In summary, understand that coupled AC energy presents threats, not only to our pipeline, but to our personnel. And personnel could be our own employees as well as the general public. Second, we have tools available to us. By strategically combining those tools, we can come up with a laminated approach, a laminated system, integrated system that can be very, very effective in controlling that threat. We're going to need to monitor those devices to make sure that they're functioning as intended, so make sure that we include monitoring in that process as well. So that brings us to the end. I'm going to turn it back over to Dan and see if we have any questions.
Thanks, Clay. While we wait for the questions to keep coming in, I just want to remind everybody, thank you for joining us on part 1 or part 2 or both for this webinar series. There will be a follow-up email containing instructions on how to access the recordings for these webinars. As you can see below, there's Clay's contact information. And again, this webinar is brought to you by Bass Engineering and American Innovations. So with that, we'll get to the first question of the day. What is the difference between PCR and SSD except for values of current? So key points between PCR and SSD.
That's a great question. Essentially, those devices are the same. They're going to block DC and they're going to pass AC. So you're exactly right in that the SSDs will have smaller values of current associated with them, while the PCRs will have larger values of current associated with them.
Awesome, thanks. Next question is, can you please elaborate on the coupon? There's a combined 101 centimeter squared coupon. What is the need for each?
Again, excellent question. And not knowing exactly what the level of understanding of coupon technology is, I may answer in more detail than you want, but essentially understand the principle of a coupon test station is to simulate a holiday or break in the coating on the pipeline. So the two 100 centimeter coupons in this particular model are designed to represent a holiday on the coating of 100 square centimeters in size. Now that's a fairly large defect in your coating. The bottom coupon is designated as the test coupon, while the top coupon, 100 square centimeter coupon, is designated as the native state coupon. So by using those two coupons, you can establish a native state pipe to soil potential that could be expected with that metal in that soil at that location. The test coupon, the bottom coupon, will be intentionally connected to the pipeline through the test head. So with that, the coupon is now exposed to cathodic protection current, the same cathodic protection current that's afforded your pipeline. So by measuring the potential on the coupon, you have a reasonable level of understanding of what pipe to soil potential you could maintain if you had a holiday equal to 100 square centimeters in surface area. Now, obviously, that's an own potential measurement when you take that measurement through the coupon test station. We all understand that we need to be looking for polarized potentials. The simple way to gather the polarized potential on that coupon is to interrupt the coupon connection to the pipeline, because that effectively eliminates the current that's collecting on that coupon. So there's a switch in that coupon head. It's a normally closed switch, and it's spring-loaded, but as you depress that switch, you're disconnecting the coupon from the pipeline so that you can get that instantaneous disconnection and thus that polarized potential associated with that coupon. So hopefully that answers your question on the DC side of the picture. Now let's move over to that single 1 square centimeter coupon that's located on the top of that assembly. The 1 square centimeter coupon is obviously 100 times smaller than those DC coupons. The 1 square centimeter coupon is migrating to the de facto standard for AC current density measurements. So with that, this particular model gives you that de facto standard, and if your AC coupon is connected to your pipeline, you need to think of that as a 1 square centimeter holiday on your pipeline. If there's any AC energy on your pipeline, it wants to come off. So it would use that 1 square centimeter coupon as a discharge point. Well, if I know the surface area of that 1 square centimeter, which I do, and if I could measure the current flowing from the pipeline to the coupon, and I know it's AC current flow, folks, but just picture the current leaving the pipe, then if I could measure that with a simple calculation, I could convert that current measurement to a current density measurement simply by dividing the current by the surface area of 1 square centimeter. From there, we can then calculate the amps per square meter and compare that to the industry standards that we shared with you in part 1, namely 20 amps per square centimeter or less are considered no threat of AC corrosion, while anything from 20 to 100 we're not sure, and anything in excess of 100 amps per square meter we would consider a threat of AC corrosion being present. A long answer to a short question. I hope we hit some. I hope we answered the question in that.
Well, great. Thanks, Clay. Next question we got. If using casings as drain points, do you recommend gradient control mats around vent pipes for personnel protection?
Absolutely. And it's a great question, and it's probably one of the finer points that can be overlooked. Since you're going to use a decoupler in connection with that installation, that means that someone's going to need to come check that from time to time. Well, since you're exposing that tester to that environment, you absolutely want to provide a gradient control mat for that individual to be standing on while he maintains that decoupling device. The same is true for any impressed current systems that you might have along that particular stretch of your right-of-way. That's another area that we didn't address in the presentation, but we often find overlooked in ACLM system designs. We will have rectifiers, impressed current cathodic protection systems installed, and while there may be some AC mitigation along the system, there's no gradient control mat around that rectifier. And so we highly recommend that gradient control mats be incorporated in your overall ACLM system design, not overlooking casing connections and rectifier installations or other cathodic protection installations.
Thanks. For the next question, when using an SSD with a gradient control mat, do you take into account the CP voltage of the pipeline or the CP voltage of the gradient control mat for the proper SSD?
Again, these are great questions. The overall potential will be it'll be a mixed potential, because your gradient control mat is essentially going to exist at something around negative 1100 millivolts, because it is zinc. But it's going to have imperfections on it. You're going to have some bare steel exposed and things of that nature. So as you connect the pipeline to the gradient control mat, and I think the question is directed to if I have a I've lost my word here, but if I have an equal voltage reading rated SSD, obviously it won't matter a lot which side I connect to which. But if I have an offset SSD spec, then I do need to know where my more electronegative potential is and where my more electropositive potential is. So in this case, you would assume that that gradient control mat is going to be somewhere close to negative 1100 millivolts. In practice, it's probably going to be closer to something around negative 1000. Even with the magnesium, with the magnesium anodes attached, you're going to see that potential come up or be more electronegative on those gradient control mats, because we're going to maintain those gradient control mats at something more electronegative than minus 1100 millivolts. So it's very common to see your gradient control mats at something around negative 1200 millivolts or more electronegative. So keep that in mind if you have unbalanced SSDs that you're installing.
Thanks, Clay. And for our last question of the day, wouldn't a casing being used as an AC drainage point face accelerated corrosion?
The short answer is yes. You would be intentionally corroding your road casing if you used it as a part of your AC mitigation system. How critical that is to your operation, I would leave that up to your own individual companies to decide. But I know for a number of folks, with casings not being mandated for a number of crossings, the road casings can serve as an active part of our AC mitigation systems without reducing the integrity of the overall pipeline system.
Awesome. Well, we got a lot of questions in today, and for the ones we didn't get to, I'll make sure that Clay or Jordan follows up with you guys individually. I'd like to thank you guys for joining us today for this joint webinar by Bass Engineering and American Innovations. Again, there will be a follow-up email containing instructions on how to access the recording of these webinars, and enjoy the rest of your day. Thank you.